And so that was the beginning of the dark side.
Yeah, that was the beginning of
Okay,
the dark
so
side.
PDEs, partial differential equations. What is that?
So partial differential equations are specific types of equations. So maybe we take a step back and just think about like equations in general. What's like the first kind of equation that pops into your mind? It might be something like an algebraic equation. Um, the like a basic example of an algebraic equation would be like a quadratic, right? In two variables. So you have like an x and a y, and there's like a quadratic in the x variable, and it's equal to y or something like that. And the solution is like is this function. You could write y as a function of x or something like that. You could plot it. You get this nice shape of a parabola. That's all well and good. Kind of one step up from that would be what we might call an ordinary differential equation. To distinguish it from a partial differential equation, we call it ordinary. And that means it's a differential equation in one variable. What do I mean by a differential equation? That would be an equation that relates a function to one or multiple of its derivatives. So, kind of the basic example of a differential equation would be like the derivative of a function is equal to the function itself, right? The if anyone in the audience has taken even a first calculus course, they know about derivatives and they know a function. They probably know a function that is equal to its own derivative, and that would be e to the x, right? The exponential
Exponential
function.
function. Yeah.
Yeah. But in fact, there's a whole family of functions that have this property, and it's just taking that exponential function and multiplying it by some arbitrary constant, right? So if you have 2 e to the x, if you take its derivative, you'll also get 2 e to the x, and so it's also equal to its own derivative. Pi e to the x, you could put any constant in front there and it'll work. So when you have a differential equation, you get if that's all you have, you get a family of functions as solutions. And if you want to fix one particular function as a solution, you need to provide an initial condition, is what it's usually called, which is just that at some point we know the function takes some value. So at 0, it takes the value of 1. Then we can fix that arbitrary constant out front to be 1 in that case, because e to the x is 1 at 0.
So out of the family of all those solutions, if I have some initial data that helps me choose which one is appropriate for the setting.
Yeah, that's exactly
Okay.
right. So oftentimes ordinary differential equations you're provided the equation itself, but you're also given another piece of information, that initial condition, which helps you fix the solution to be one function, right? Okay, so now let's abstract up one more level and talk about partial differential equations. So these are differential equations where the function has more than one variable. So when a function has more than one variable, you can take a derivative on any one of its variables. And we call those partial derivatives to like distinguish them from the fact that the function is not just of one variable and it's totally described by its derivative. It's one derivative, right? There's multiple derivatives. So if you only have one derivative, you only have like a partial of the information. You only have the amount of information to describe the function. So I guess that's why it's called a partial derivative. I don't really know what the
So if
what the
I'm going
history is.
like northeast, I can ask how fast am I going in the east direction, or how fast am I going in the
Yeah,
north?
yeah. If you want to think of derivatives as rate of changes like that, yeah. If you describe information about how fast you're going east, you don't have information about how fast you're going north. You would need also that information in order to describe your motion totally. Um, so yeah, partial differential equations are differential equations where the functions have multiple variables, and so you might have different derivatives. Kind of the basic example is a function that is a function of two variables, one that we call space and one that we call time, right? And so that would be it. And then if we had a differential equation that related the space and time derivatives, uh, that would be a partial differential equation. And
So
we could,
what's an example of a partial differential equation?
that's a great question. So super common examples that come from undergraduate physics. In fact, I was thinking about it earlier. So much of undergraduate physics is really just PDEs, solving partial differential equations. Um, One that is really basic, but usually sometimes it shows up in like a statistical mechanics or thermodynamics course would be the heat or diffusion equation, which describes a diffusion of heat through some medium. So as an example, if you take a metal rod and you suspend it over a fire in the middle, and you start heating the metal rod in the middle, but you leave the ends unexposed to the fire, you'll get a temperature profile on the rod where there's high temperature in the middle, and as you go out towards the ends, it's low temperature. You can describe that with a function of the spatial coordinate along the rod, right?
And what about
And
the time coordinate here?
in the time coordinate, the heat equation would tell you how that how that temperature profile changes in time. So if you know that initial temperature profile, you can use the heat equation to tell you what the temperature profile looks like at some later time. So in that case, there's two spatial derivatives related to one time derivative. That's just the nature of that equation. You can go look it up on Wikipedia, the heat equation, if you want to know the exact equation. Yeah, so this is how this goes generally. And like I said there, the initial condition in this case is usually a function of one variable, and you ask how that initial condition results in a solution that changes in the other variable.
Typically, we also hear of boundary conditions. What's the difference between a boundary condition and an initial condition?
Yeah, that's a great point. So the boundary conditions, if you have our rod is finite in this example, right? Our rod is finite, and so we have to prescribe the derivatives aren't well defined at the ends because you only have information from one side. So you have to usually prescribe in that case what's happening at the endpoints. In this case, they're exposed to the temperature of the air. So the temperature at the endpoints would be fixed to whatever the temperature is of the air. And so that would be in the mathematics, it becomes conditions on the values of the function at the two endpoints. And that's why we call them boundary conditions, because they're at the boundary of our domain of interest, which is the rod in this case. So some other common examples would be the wave equation, which is an equation that describes small perturbations in elastic medium. You can think of that as like vibrations on a guitar string. If you pluck the guitar string in a certain place, when you're holding it back right before you let go, you've provided an initial condition that is the displacement of that string. And as you let it go, it will evolve under the wave equation, and that'll tell you how the string vibrates and how you generate the sound that you hear when a guitar is strummed, right? So in that case, it's actually two spatial derivatives and two time derivatives that are related to each other. And in that case, also the boundary conditions would be fixed. There are other different types of boundary conditions, though. It could be that the derivatives at the ends are set to zero, or we could say if we had a string that was connected at the ends, we can set the value at one end to the value at the other, and it would be some continuum boundary conditions that it actually lives on a loop or something like that.
So there's sort of periodicity happening there.
Yeah. Often you call those periodic boundary conditions because you require that at one end it's equal to the other, and then you think of it as being on a circle, and it has to then be periodic.
So taking that
Period
example of the
circle.
wave equation, when I teach introductory physics, I usually have an example of a guitar string, and I tell them that one can excite different harmonics on the guitar string. And typically what I show them is that it's a sum of the harmonics that ends up being displayed on the guitar string and not one harmonic. And somehow you can add together different harmonics and get a final shape on the guitar string. Why does that work for a guitar string? How can
Yeah,
I just
so
add up together harmonics and I get the right answer?
that is an incredible question because all these equations, both the heat equation and the wave equation that we've talked about so far, are examples of linear partial differential equations. And linear just means that there's only ever sort of one function that shows up in a term. It's a sum of a couple terms, and one function, it might show up with some derivatives, but it's only one function there. And this means that if I take two separate solutions that I've found individually to the partial differential equation, I can take their sum and I can show that because derivatives split over sums and the equation is itself a sum of some derivatives of the function, that the sum of the solutions separately is also a solution, right? So in the case of these harmonics, oftentimes what we want to do is decompose some complicated initial condition into some simpler ones that we might have a way of solving the time dynamics for. And then if we take those solutions and add them back up, they solve the complicated initial condition evolved through time under the partial differential equation.